So in this problem, we're giving some BET data. So we plotted the data given the linearized plot that I mentioned earlier. And we're given a few other things. We're given what is the heat of vaporization of nitrogen. We're given the temperature the experiment was performed at. And we're given how much powdered silica we absorbed the nitrogen onto. Okay. And there's one other piece of data that we would need to be given to actually work this. Let's put this down here as another given. And that's nitrogen, when it sits on silica, occupies a known amount of area. So each molecule occupies about 0.0162 nanometers squared. Okay, so that's actually also given. Okay, so given that, we're supposed to figure out what is the desorption enthalpy for hydrogen from this type of silica, and also what is the specific surface area. So how many meters squared per gram for this powder. All right, so we know the slope is equal to C minus 1 over C times N star. So we can solve and we know that the y-intercept is just 1 over C times N star. So we've got two unknowns here, but if we divide these, we can see that if we just take the slope and divide it by the y-intercept, the C N star is going to cancel, and we're going to be left with just C minus 1. And so we can solve for C. So C is equal to 1 plus the slope over to the intercept. I'll just call that B. Okay, great. So let's put those numbers in. So we said that the slope was 319 reciprocal moles, and the y-intercept was 3.35 reciprocal moles. And so that comes out to 96.2. For C, remember that C is equal to an exponential, that's the desorption enthalpy. So we have the heat of vaporization was equal to 5.6 kilojoules. So we'll just convert this on over to joules. And then we had R 8.314 joules per mole per Kelvin. And we were at 77 kelvins. And we've got the log of C, which was 96.2. Okay, so we plug in a 96.2 here, and we end up with the heat of desorption is equal to 8.52 kilojoules per mole. So as we expect, it's going to be more than the heat of vaporization. To find the specific area, we know that the area is going to be the number of molecules that are adsorbed times the area that each one takes up on the surface. And we could say that is going to be the number of moles that we could, the max amount that we could absorb to get monolayer coverage N star, multiply that times Avogadro's number. So this is going to be the same as that, right? The number of molecules that we could possibly put on to make a monolayer is the number of moles that we could put on to make a monolayer times Avogadro's number. So if we multiply that times the head group area, or the adsorption area, we would actually have the area that's been absorbed. But we need to find N star first. And we can get that by remembering that the y-intercept was the reciprocal of C times n star. And we already calculated C, so we can just solve for n star. So n star is just going to be 1 over the y-intercept times C. And so we can plug in our value for those two numbers. So the y-intercept was 3.35 reciprocal moles. And C was a pure number. We said it was 96.2. And so we're going to end up with a number of moles, which is fortunate. That's what we want. And so we get n star is going to be 0.0031 mole. And then we can plug that in up there. So if we do that, we get the area that we can cover with nitrogen molecules is going to be the number of moles of nitrogen molecules we could put on there, assuming just monolayer coverage. Avogadro's number, 6.02 times 10 to the 23rd per mole. That's ugly. Let's fix that. 10 to the 23rd per mole. And then we have our A naught, which we said was 0.162 nanometers squared. So if we multiply all that together, the area is going to be 3 times 10 to the 20th nanometers squared, or we could just remember that a nanometer is going to be 10 to the negative 9, and we square it, that's 10 to the negative 18 is our conversion factor. So we end up with 300 meters squared is our area, but that's not what we were looking for. We were looking for the specific area. So the specific area is just per mass of powder, or per mass of solid. So it's area, the surface area divided by the mass of the solid. Or the mass of the solid, I'll just put adsorbent. Okay, so we already know what that is. We have 300 for our area, and we had 0.75 grams of solid. So we divide 300 by 0.75, and that results in 400 meters squared per gram. And that is our specific area. And that's typical for mesoporous silica, such as MCM41.